Now, what do we really gain from this? And it's amazing what we have gained from this. There was a recent review by Lane and Martin, and yeah, it's a complicated slide. Don't worry about it too much about the details. What they did is they did a bioenergetic analysis of different species. And what they found is that, yeah, bacteria like E. coli are phenomenally efficient at consuming things and churning out energy. So if we want to do something like, if we want to make a vat that's producing lots and lots of insulin, it turns out the best, most efficient way to do that is put the insulin gene inside of a bacterium because, look at us. We're not very good at this because we've got all these other organs that are busy doing other things. Bacteria can concentrate wonderfully on the production of this one particular gene product. So, a lot of efficiency there. And when you look at the life history of bacteria, they live in a regime where efficiency and rapidity of reproduction are paramount. And so what's going on when you look at their evolution is that there's been lots of evolution honing them for efficiency, for small genomes, for being able to reproduce rapidly. Now when you look at eukaryotes, like this one at the bottom here, what you find is something different. Now here you've got a eukaryote. It has adopted mitochondria that do all of its energy production, and it has many mitochondria in the cell. So we've got lots and lots of mitochondria all sitting there producing lots and lots of energy. In the world of a eukaryote, we have surpluses of energy. We got more energy coming in than we know what to do with. And we can invest this in other things besides just blind, empty reproduction. And what this analysis shows is that, when you ask, okay, well, just how much energy does a cell produce? And you look up there at the top graph, Escherichia, the E. coli, yeah, they produce lots of energy per gram of cells. They're really good at that. But when you look at energy per genome, because we've outsourced all of our energy production to these little tiny genomes that are found in the mitochondria, that means our genome has a huge surplus of energy, and that we can afford to be really sloppy with our genomes. And we can start doing things like making lots of extra genes that do specialized stuff without losing out in the race, without losing the competition that prokaryotes are into. So what this allows us to do is it didn't just provide us lots of energy, it basically gave the genome leisure time so it could pursue other things, like building elaborate genomes that allow us to react to the environment in sophisticated ways, that allow us to build multicellular organisms, that allow us to specialize, so that we can, for instance, build livers and kidneys and brains, in addition just to raw cytoplasm and reproductive material. And this is all coming from mitochondria. What a wonderful thing. This is what makes us human. It's what potentiated the human experience, is having this excess of energy. So this is really my second major point that I want to get across here, is that when you look at the history of life on Earth, what you find is that, yes, competition is important. Competition hones the efficiency of organisms. It makes them more and more functional. But when you look for true revolutions, when you look for things that have radically changed how life operates on the planet, look to cooperation. There was probably something pretty major in a cooperative event that allowed this explosion of novelty. And this is one of the best examples, is this acquisition of mitochondria. Now I want to talk about another example here of wonderful things that have happened in the history of life. And for that, I want to heap praise upon worms. Now, you've all heard of the Cambrian explosion, right? Okay, a few voices. Okay, yes. All right. So about 500 million years ago, there was this burst of evolutionary creativity that all of a sudden, all the major animal forms that we are now familiar with had their origin in roughly this Cambrian period about 500 million years ago. So arthropods, insects, crustaceans, trilobites, all these creatures, as well as mollusks and chordates and lots of these various worms that you find, evolved first in the Cambrian and then diversified over time to produce us eventually. Yeah, it took about 500 million years to make us, but yeah, we're worth it. But I think that the real revolution, the real change that occurred was pre-Cambrian, and that was the evolution of worms. Worms are hugely important. They're underappreciated. They're the greatest thing that ever happened to the planet, aside from mitochondria. Okay, mitochondria enabled worms. Worms then enabled this thing called the Cambrian bioturbation revolution. Now, first let me define a few terms. What is a worm? A worm looks like this. A worm is a simple tube. It's an animal that can burrow. It's usually got a simple skeleton, in this case a hydrostatic skeleton, so it's got a little pressure inside of it, so it's got some rigidity and it can push its way through substrates. What this is a diagram of what we think the Precambrian worms sort of looked like. Now, this is a worm from 600 million years ago. We don't have fossils of this. Okay? It was tiny, it was gooey. We're not going to find many of these in the fossil record. Maybe someday we'll get lucky and we'll run across a few, but no, this has not been found in the fossil record. Where it's been found is in the molecular record. And what this is a diagram generated by looking at many different organisms and asking, okay, what do they have in common? And for instance, if you ask about flies and people both have hearts. Yay. They're a little different. But when you get down in the embryology, that evo-devo stuff, and you ask, where does the heart come from? You discover we have something in common. We use this NKX 2.5 gene to initiate heart formation. And that's true of us, it's true of fruit flies. So you can sort of guess the last common ancestor of humans and fruit flies would have had NKX 2.5. A version of NKX 2.5, it would have had something like a primitive heart. Similarly, MyoD, that's the gene that initiates muscle differentiation in us and flies. So the last common ancestor would have had this. And there's these Hox genes that partition the link to the animal and give us positional information. Those would have been there in that last common ancestor. So we can say, okay, the last common ancestor of all of us animals would have been a worm-like creature that expressed these particular genes in a minimalist sort of pattern. And that minimalist pattern would have looked rather worm-like, like this. And this would have been an animal that could have burrowed through the environment and done interesting things. And burrowing is the key thing here. What happened there? Well, the bioturbation revolution refers to this. What's going on here is that before the Cambrian, the world looks like this. If you go out, if you could get in your time machine and fly back there and take a look at the Cambrian seas, the Precambrian seas, what you would have found in the shallow seas is sheets of mud and things like algae growing on it and frond-like things growing on the surface. It's all diagrammed up there, where what you've got is everything is growing on the surface. And over time, those sediments build up and get thicker and thicker. And in those environments, a lot of the minerals, a lot of the resources end up locked up deep in these sediments. And only when something like a storm or earthquake comes along does it get jarred up and things get freed up. And all of the growth is going on in the surface, which is fine. You can get some flourishing of the environment there. What the bioturbation revolution refers to is this phenomenon over here on the right. You got worms, and worms violate the integrity of the soil. We know this. This is what they do. And what they do is they take these nice sediments that have been building up for millions of years, and they start digging into them and excavating and finding lots and lots of good, tasty things down there. And so in the Cambrian and in the Precambrian, what's happening is worms are busily churning up these sediments in the oceans and spewing them up to the surface. And suddenly this locked up wealth is liberated and it's available for everything. And this leads to a radical change in what life can do. I think this is probably the phenomenon, along with increasing oxygen content in the atmosphere and the seas, that fueled that Cambrian explosion. Is all of a sudden worms are liberating lots and lots of resources. Instead of it being buried, now it's all exposed, it's up here for everything to live on. And what that leads to is the Cambrian explosion, which has all these strange creatures scurrying all over the place and doing all kinds of interesting things. And, and from our point of view, existing as our ancestors and eventually producing us. So what they're doing is they're taking advantage of the fruits of all this death. Now what's going on here is also familiar to us in modern day, and that is that what this enabled was deeper trophic webs. I'm using another jargon word here. trophic webs, food webs. What these are interlocking patterns of organisms that work together to take advantage of the resources in the environment. So I illustrate here is a very simplified diagram of an Arctic food web where there are all these creatures and they're eating each other and they're eating each other's excreta and they're parasitizing each other and they're decomposers living off the dead things. And all of those working together build this huge depth of life. It's not just a flattened life pattern where you've got one kind of organism living off of the environment. You've got this ecological diversity. And it turns out this is incredibly efficient. This is the way to generate a rich world, is to have a very deep food web where you have lots of different species, lots of diversity, all flourishing and all taking advantage of different aspects of it. I want to make a contrast here that this, for instance, is where I live. Well, ideally, this is where I live. These are the Midwestern prairies of the United States, and this is what they look like when they're undisturbed by human beings. And it's a phenomenon just like those Precambrian seas. If you ever visit the Midwest, you visit our farmers, they are so proud to take you out to their farm because you dig there and the topsoil is amazing. It's 10,000 years worth of accumulated topsoil. It's rich, it's black, it's beautiful, it's nice and crumbly, it's moist. That's why this is the breadbasket of America, is because, man, you can grow anything in this beautiful environment. And it's been the environment where prairies have thrived, where grasses have grown for thousands of years since the retreat of the glaciers. So this is one kind of environment, but I want to contrast that with this tropical rainforest environment. And what you find in a tropical rainforest is something very different. If you go to the rainforest, you will not find native guides who will lead you through it and tell you about how wonderfully rich the soil is, because it's not. It's thin and it's acidic and it's not very great soil. But there's a reason for that, and that's because instead of locking up nutrients in the soil, in places like tropical rainforests, those nutrients have been thrown up into the sky. Then what you find is jungle. You find trees that are soaring up there. You find all kinds of different species thriving at all levels of this particular environment. Instead of locking up the nutrients in the soil, what you are instead doing is putting them into dynamic flux in this complex environment, this diverse collection of species that are all thriving and building this wonderful environment there. So this is one way to look at it, is that diversity is a good thing. If you want to talk about efficient use of resources, the best thing you can have is a great diversity of different forms using those resources. They will milk everything out of it that you can, and they'll throw it back into the environment in these beautiful cycles. So one message I want to give here is that in addition to diversity, what we can see when we look at the history of life on this planet is that life can change the world. Look at what worms did. Worms transformed the planet and made it a rich place for everything else to thrive in. That they are the base of exploiting these resources for lots of different organisms. And another point is simply that diversity is much richer than uniformity. That what we want is a variety of different forms. If we want to really take advantage of the environment, we need that. Now, unfortunately, of course, when you look at these environments nowadays, you'll find that we are busy flattening them as quickly as we can. I said, this is where I live, Midwestern prairie. It actually isn't, because all those rich species that thrive in the prairie environment have been plowed away. And if I showed you a current picture of that same region, it would be fields and fields of corn, nothing but corn. Corn growing everywhere. And right now, of course, when you go to the tropics, what you discover is that people are busily burning that down, destroying all that diversity, and instead replacing it with things like fields of sugar cane. Again, nothing but sugar cane everywhere. It's very sad. But diversity, it's important. We should be valuing it more. Okay, one other thing I want to talk about is another value that we find in evolutionary biology that tends to be underestimated by many people, but it hasn't always been. And I got to mention Peter Kropotkin. Hello? Oh, I'm wrong. Wake up.